Mattia is the next speaker, Mattia Porchetta from Tremec. Mattia has worked as a development engineer at Tremec Belgium since 2018. He is responsible for oil management and CFD simulation by means of Particleworks. He holds a master's degree in mechanical engineering with focus on internal combustion engine and turbo machinery from Politecnico di Milano. During his master thesis, he worked on laminar to turbulent transition prediction for turbo machinery application by means of open source codes. He also holds a master in motorsport aerodynamics from Dallara Automobili with focus on CFD and wind tunnel testing. Yeah.
Thank you for the introduction, Massimo. Happy to be here, and today I will present a couple of test cases. Actually, they're not the latest results that we have, but I will say old but gold. Since that moment, we built confidence in the software and in the correlation between the software and test results. And we consistently introduce the use of Particleworks in our daily routine, I will say. Here we have a short summary of what I'm gonna introduce. So I will first say who's Tremec. Then I will talk about oil management within the company. So what do we do? What are the activities that we do to develop our products? And then we will go into the two test cases. There will not be a lot of technical information. I mostly focus on the comparison between test results and simulation results, but feel free to ask it. So who's Tremec? Tremec is a company that develops gearboxes, mostly for high power and high torque applications. It has 3 facilities. Actually, the headquarters is in Mexico, in Querétaro, and there they develop and they produce the manual gearboxes. They are quite popular on the American market. Then in Belgium, we have the R&D department where we develop the DCT gearboxes. It's fairly new, so since 2016 that we have the facility in Belgium, and the last facility is the one in the States in Wixom, where we have our production line for the DCTs. So these are the 2 DCTs. One is a 7-speed, the other one is an 8-speed, and you can find them in these 3 cars. So the Shelby GT500, the new Maserati, the MST20, and the new Corvettes. During the last year, we also, let's say, further developed these 2 products, the DCTs, and into hybrid products. But then, because of the market change and latest trend during the last years, we are focusing on fully electric solutions. So we're focusing on EDUs solutions. Okay, just some details about the 2 DCT transmissions that will be also the subjects of the 2 test cases. So we have the TR97T, that is a 7-speed dual clutch gearbox, and then the TR9080, that is a transaxle transmission. They both more or less can handle up to 1,000 Nm input shifts in less than 80 milliseconds. The main difference between the 2, okay, apart from the number of gears, is that the transaxle one also has the MLST and ELST. So what we're focusing on right now is an EV solution, so an EDU solution, comprehensive of inverter, motors, and gearboxes. The target is still for the high power, high torque applications. I will say fairly power dense, so we will try to have a compact product with up to 600 kilowatts. And also another goal that we are trying to achieve is to not only be able to reach high power, but stay there for a sustained period of time, and still guaranteeing a fairly high efficiency above 90% in the WLTP cycles. So what do we mean for oil management, or what do we do? as an oil management activity inside of Tremec? Well, starting with lubrication, of course, we take care of the lubrications. We need to take care that all the gears, bearings, seals, all the mechanical components that need to be lubricated, receive enough oil. And well, not only we want to minimize the wear, but if we're able to optimize the lubrication inside of the gearbox, we can also obtain an high efficiency. So efficiency, again, it's important because of all the regulations that we have, the WLTP, but for high power applications, if we optimize the efficiency, we can reduce the thermal losses, and we can achieve, for example, very high speeds, and meaning that we can downsize, for example, the cooling circuit or simplify the cooling circuit without requesting too high flow rates. Last point to close this cycle, let's say, because all these points are correlated one to the other, is the actuation and pump feeding. So we need an hydraulic circuit to activate, perform synchro shifts, or in order to distribute the oil for cooling. We need the pump, and it's challenging. For example, during high performance application, because of the high lateral G and longitudinal G, the oil will move within the gearbox, and there is high risk of exposing the inlet of the filter to the air that can cause, like we will see, oil starvation or suction issue. Last point that we need to take care is the air venting. So normally in gearboxes we have a breather or a venting tube that's needed to balance the pressure inside and outside of the gearbox. So keeping ambient pressure inside of the gearbox. How do we achieve all of this? Sorry, I drink. So normally the ideal cycle that we'd like to follow to achieve those goals is to start with simulations, and the software we use is Particleworks. Then once we are confident enough with the first concept, we move to the prototypes stage, and normally here we test on benches. The bench you see on that image is a very capable bench at Toyota Motorsport. Why I say very capable? Because it's capable to mimic the angle of the oil inside of the gearbox by tilting the gearbox along the pitch and roll axis. It can achieve very high angle and also with a very quick rate of change. You can also control the input speed up to 18,000 RPMs. And the last test, of course, when you are happy with the prototype, normally then you start developing your product intent solution, and finally you will be testing in the vehicle. Of course, as you see with the arrows, the best time to implement changes is during the simulation phase or concept phase, is the cheapest and the most flexible. And while going to the last one, that the test on vehicle, it's very expensive, and you have, let's say, almost no margin to implement changes during the test. For example, if you rent a truck, you don't want to keep your car in the garage to change some parts, and also because sometimes it's very difficult or even impossible. So on the right, you already see a simulation. That's okay. It's the TR9070 transmission. We'll start talking about the suction issue. Yeah, you see a simulation of more or less of the complete system. But actually, when we had this issue, we didn't have the software, and we were close to the production phase. And we found this issue during a track test. So the track test was the Gingerman track, and during a specific corner, because of the hard braking and corner into the left, there was no oil that was reaching the inlet of the filter, and we were causing oil starvation. That was inducing a system pressure drop in the system with a consequent loss of traction. So we were not able to deliver power to the wheels. And at the time, we didn't have the software. We had a lot of pressure because we were close to production. And it was really difficult to find a solution because the slots on those benches are very few. Sometimes you have 1 or 2 per year. Again, testing on track was really, really difficult. And yeah, so that's why we decided then to try Particleworks. And our goal was to simulate the same profile where we were having issue on track, including all the speeds of the rotating gears and the acceleration at the system level, full system level. Okay, here's just a simple sketch with paint, just to say that. So during the simulation, we simulated all. So it's a full system simulation, but we're not simulating the internals of the hydraulics. For those that are familiar with Particleworks, maybe they know it already. For those that are not, so what we are doing here, we take the hydraulics as a black box. We close them essentially. We have a pump function that will push, add momentum to the particles and push them towards some outlet functions, and then these outlet functions are connected to the inlets. Okay, so on the left here, we have the test on the bench, on the dynamic tilt test bench. This is a view from the bottom. We had a transparent sump, and on the right we have the simulations, so a bottom view. And graphs on the bottom, we will talk about them later. So what was happening is that during the hard braking and current to the left, the oil was moving along the surface of the sampan and was leaving the inlet of the filter exposed to the air. And this was causing the suction issue. So the red line that we see here is the measured system pressure during the test. What we see is that we have some system pressure oscillations followed by a big pressure dip, and this was causing the clutches to open. As we can see, so I will say we had a good correlation from a qualitative point of view between the simulations and the test. Of course, in the test we have some oil films that is not catched by the simulations, but if you look at the oil distribution, for example, this angle and this angle, and also, yeah, the angle here is more or less the same. Another, let's say, quantitative correlation that we had is between the flow rate measurement in the CFD simulation and the system pressure drop. In both cases, we have 2 drops, a small dip followed by a deeper one. The only thing is that we have a delay in time between the 2, but it's also true that the flow rate measurement is at the inlet of the filter, while the pressure drop is measured downstream in the hydraulic circuit. So what did we do to solve this issue? Again, we were close to production, didn't have a lot of time to implement big changes, so we focused on the sampan, and the idea was to introduce some fins, trying to force the oil to stay close to the center of the pickup, well, where the pickup location is. We did some optimizations of these fins. We tested different configurations, and in the end, this was the best configuration that was not too close also to the inlet of the filter. There is some margin. And here we have a comparison. Unfortunately, I don't have a picture with transparent sump with fins, but here on the left, we have the sampan without fins in CFD, and here is a sampan with the fins still in CFD. And yeah, immediately switch to this configuration. It's clearly visible that the fins are helping in keeping the oil close to the center. This kind of swirling motion is reduced, and it was verified on bench. So in this case, these are both system pressure measurement on bench. The blue one is the case with the fins, and this big dip that we had before, now it disappeared. And same as in CFD. So the blue line is the solution with the fins. We still had two small drops, but more or less same in magnitude. And the second big dip that was causing the clutches to open was solved. And yeah, this is how we solved the solution, and we were very happy because until that moment, the gearbox for us was kind of a black box. We were not able to visualize what was happening. The second test case is the one related to the tier 9080. And yeah, I call it oil expulsion. So what was happening, here we have the breather and the oil was coming out of the breather. The main difference between this test case and the one before is that in this condition, so actually we found the issue first during the simulation. So in this case, we were still during the concept phase, and we were able to spot the issue, spot the criticalities in the gearbox, prepare for the next tests, and already implement a solution and validate it. As we see from the bottom here, we have again a track profile. It was a quite demanding one, and it's also very long. And one of the greatest value that we found in Particleworks was that we were capable of simulating almost 48 seconds in 5 days and obtaining some results. So at the time for us, it was, I would say, great, and perform also many different iterations. And for this specific case, to give you some values, so it was about 1.3 million particles. Particle size was 2 millimeters. So we had at least 5 particles per passage. We also did some refinements and some, I would say, particle size sensitivity studies, but 2 millimeters was working fine for this kind of applications and mostly for the oil motion. So what was happening in this case, here we have the SAV room, that is where we have the actuation valves. The SAV room was connected to the sampan and to the rear housing by 2 passages. The oil was going in during some conditions, and eventually during severe braking it was coming out of the breather. That's really risky if it happens in the car, because the car can catch fire. And here we have the validation with the test results. So what we see here is again the profile. Here we have some temperature measurements. What was the idea? We had a plastic tube connected to the breather with 2 thermocouples. And when the oil was coming out, the 2 thermocouples measured a spike, an increase in temperature. While here we have the flow rate measured in CFD. And in this case, although it's a very long maneuver, there is a very good correlation between the CFD and the test results. They are almost on spot. Again, there is just some delays in this temperature measurement, but again, the thermocouples are downstream of the location where we measure the flow rate and the oil coming out. And yeah, okay, then also visual assessment, you can clearly see the oil on the paper. So very good agreement for a very long maneuver. What was the solution in this case? Well, it was fairly easy. We needed to isolate the SAV room for the passage to the sump. So this is a bottom view. We added 1 flap, so it's a rubber flap, in order to allow the oil to come out from the SAV to the sump, but not the other way around. So normally this is a deformable piece, so it's a rubber piece, and we had to introduce some simplifications. So what we did, we simulated it as a solid body in Particleworks. We added some hinges, and in order to use this, let's say, modelization, we need to rework the geometry in order to have at least 3 particles along the thickness. So this part can rotate along this axis, and it worked fine for us for the simulation. Okay, in the other solution, the passage to the rear was completely sealed, and then since in the SAV room we had the breather, we needed to add an extra air passage that is feature A3. And here you can see the bench in action. It's quite extreme. This is again at Toyota. Correlation was again really good. I don't have a video of a transparent feature on this side, but in CFD, what happened is that the oil level in the SAV room decreased and went almost to zero. And then we did also the verification with the thermocouples and with the paper. And as you can see, there was no oil in there. So as a conclusion, what I can say is that since we introduced the software, there was massive difference in our routine. Again, for the first issue, the suction issue, we were spending almost 5 months trying to solve it and without succeeding in it. Well, then, since we ran the first simulation in 1 month, we had an idea of a possible solution. The time to prototyping it, testing it, and the issue was gone. And since then, we always use it during the initial phase of the new concept development. And we always had very good correlation in terms of oil displacement within the gearbox compared to the test. Normally, we run simulation of about 1 to 5 days. Particle size can range from 2 millimeters to 0.1 millimeters, depending on the applications. And I can only say that it really helps us in spotting the critical areas inside of the gearbox. Just to give you some extra comments, for us, the next goal will be to focus on churning losses prediction, heat transfer prediction, same as the presentation that we saw today. I think it's all from my side. If you have any question, feel free to ask. Thanks.
Thanks for the presentation. The question is, how do you specify the breather itself, the breather part? Do you have the breather part itself, the breather opening? How do you specify it in the model? It's just a pure connection to the
breather
domain.
Opening is just a
pure opening.
Yeah, pure opening. Yes, the particles were able to potentially leave the simulation.
Okay.
And then I measured. I didn't specify. In this case, they were both single phase simulations, so just one phase, just the oil.
One question, you showed quite long simulation in terms of physical simulated time, like 50 seconds. Probably is, do you simulate a complete lap and do you use a multi-GPU?
So at the time we were using just one GPU. It was a GV100. Now we use multi-GPUs. It was not a full lap in that case, but I would say that was one of the longest circuits in Europe, if not the longest. So it was just a portion, but potentially, yes, we can simulate a full track in, now with 2 GPUs, probably 3 days, 5 days, depending on the resolution required. And then, of course, the application. In this case, we were mostly focusing on the oil distribution within different rooms inside of the gearbox. And if you have to look at churning losses, probably it's not going to be possible. Or what we did most of the time, it was sub-modeling. So from this big simulation, then we focus on different areas like the differential, the clutches, and so on, using the, let's say, full-scale simulation as inputs to
obviously the RPM of all the components and gears was time dependent according to this.
Definitely. Yes, everything was time dependent. Sometimes we also do, normally we try to mimic the same condition that we have in track or on the bench. So, if needed, of course.
Okay, thank you, Mattia.
Thank you. Grazie.